All right, so I want to do collisions in Python. And so you're going to do collisions in Python because I'm setting the rules here. Just kidding. Let's all do this together. Okay, so we want to model collisions in Python. Let's just start talking about collision just to make sure we're all on the same page. So I have two objects, A and B, moving towards each other, and they interact at some point. And we can do this a lot of different ways. But when they interact, then I have two forces. I have the force that B pushes on A, and this is momentum PA1. This is PB1. So there's the force of B on A. But since forces come in pairs, A pushes back on B with the same force. So I have this FAB. So FAB equals negative FBA. So those two forces have to be equal and opposite. That's how interactions work. So what's going to happen to object A? Well, I can use momentum. This is the only force acting on it. So if that's the case, then I can use the momentum principle for object A. FBA is delta PA delta T, where that's the change in momentum, and that's the time the force is applied, and that's going to be equal to, that's fine, let's leave it like that. But I could do the same thing over here. I could say FAB equals delta PB delta T. But these two are equal and opposite of each other. So this is going to be equal to negative delta PB delta T. Now, if A pushes on B for the same amount of time that B pushes on A, then these two delta T's are the same, and I get delta PA equals negative delta PB. And I did say, I remember, like, hey, this is a physics lessons for how to use Python, and I'm talking about physics here, but I don't know. I couldn't help myself. So then I can add that to both sides. I get delta PA plus delta PB equals 0. So this says that momentum is conserved. The momentum of this stuff before is equal to the momentum of the stuff afterwards. A is going like that. B is going like that, whatever. But here's the key. Momentum will be conserved. A collision will work as long as this is true. As long as those are the only forces acting on them. Okay, so how are we going to do that? Well, you know the answer. Come on, you know the answer. Go ahead and say it. You know the answer. The answer is springs. Springs. So before I have a model for a spring that looks like this. This is some spring with a length L0 and a spring constant K, and then I stretch it to some vector length L. And I always get this backwards, and I know that I get it backwards, so I should get it forwards, but whatever. Then I can say the force from the spring is going to be negative. Actually, so K, this minus that is positive. Yeah, it should be like this. Negative K times the magnitude of L minus L0 times L hat, where L hat's a unit vector from L to there. So that's what we're going to use. Now, we don't want to have a spring force between our two masses, but only when they overlap. So suppose I have A right here and has some radius, and then I have B over here. And then so they're going to overlap. If they overlap, I want a force pushing them apart. Okay, so I could say FA is going to be equal to, let's see, K times the overlap amount. Okay, the overlap amount. So this is RA, this is RB. So the distance between them, I can get the vector R. So R is this vector. It's going to be the vector RB, the position of object B, minus the position of object A. And then I want to take that, the magnitude of that, R, minus the distance between them, which is going to be I'll call it RA plus RB. That's the radius of the two. And so if this is smaller than that, then there will be a force pushing them apart. And then I just need to multiply that by R hat. Okay, now, And then if they're not overlapped, so I need to put a statement in there. If they're overlapped, then there is this force, and this force is this amount. And if they're not overlapped, the force is 0. And I need to do that for both balls. Now, I'm using a spring force, but you could, any force will work. I could just say if they overlap, push them apart. And actually, I'm going to start off with that. No, I'm going to start off with this, and then we'll change it. So let's go ahead and move over to Python and model this thing. And I'm going to need some numbers, and that's fine. So here we are. I'm using GlowScript v Python in Trinket. Make that a little bit bigger. Oops, a little bit bigger. Okay. So let's go ahead and start just make my 2 balls. I want to make the 2 balls, and they're going to move past each other, and they're not going to interact. And let's just do that, and then we'll make them interact. Okay, so ball A equals a sphere. Its position, I'm just, in my mind, I'm thinking of where these start off with, equals, I don't want them too far apart. So vector, they're like tennis ball sized. So let's put that about 10 centimeters. So negative 0.1, 0. Let's make it move in a line. That's what I'm going to do. So negative 0.100, and the radius is 0.02, and the color is yellow. And make trail equals true. And then ball B is just going to be sitting there at the origin. Position equals vector 0, 0, 0. Its radius is going to be slightly different. So radius equals 0.017, and it'll be cyan. Color equals color dot cyan, and also make trail equals true. Okay. Now I need to give some initial conditions for these, the velocities and the momentums. So ball A dot M, let's say it's a tennis ball. Let's say it's 100 grams. So 0.1. Ball B dot M equals 0.07. Just making up stuff here. Ball A dot P equals ball A dot M times the vector. How fast is it moving? Let's say it's moving at 0.100 meters per second. So it'll take a second to get there. Okay. That's not very fast. Let's increase that to 4. And then ball B dot P equals ball B dot M times vector 0, 0, 0. That one's at rest. K equals 500. I'm going to use that later, but I'm going to put that in there. And let's go ahead and do this. RA equals ball A dot radius. I don't want to type ball A dot radius, so I'm giving it another name. RB equals ball B dot radius. T equals 0. dt equals 0.001. And now I'm just going to model them moving past each other, and that's it. And this is a good idea to do, right? You want to kind of get things started and make sure things are working before you do anything complicated. So let's say while t is less than 2, it only take half a second to get there. Rate 1,000. So remember, this line says don't do more than 1,000 calculations per second. And since I have a time step of 0.001, this would be in real time. Okay, the first thing I'm going to do is update the position of ball A. So ball A.POS equals ball A.POS plus ball A.P times dt divided by ball A.M, right? So that's ball A.P is divided by the mass is the velocity. Now you can say, oh, you don't need to update B. Well, I'm going to. Ball B.POS equals ball B.POS plus ball B.P times dt divided by ball B.M. Now I need to update time. T equals T plus dt. I didn't even run it without. I did skip a step. I should have just ran it with just the balls, but whatever. Let's run it and see if I made. Okay, I did. I did it. Okay. Ball spring collision 1. I'm going to give you the code down below. I always give you the code, and I just covered up the animation. So let's move this up here and run it again. There, can you see that? Okay, so they didn't collide, and they went on too long. So let's change this to, let's 1.6. I don't know. Okay, so now what I want to do is to put in, I'm going to go up here and say this. FA equals vector 0, 0, 0. FB equals vector 0, 0, 0. Now I'm going to also update the momentum, even though it doesn't change. So ball A dot P equals ball A dot P plus FA times dt. Ball B dot P equals ball B dot P plus FB times dt. So nothing should change. Okay. So now I'm going to calculate the distance, the vector from A to B. So I'm going to say R equals ball B dot POS minus ball A dot POS. So that's that vector from A to B. Now I can say if mag R is less than RA plus RB, then I have a collision. And if I have a collision, I need to calculate the force. So let's say this. FA equals K times, I wrote it down over here, the magnitude of R, mag R, minus RA minus RB. So I didn't put it in parentheses. And that will tell me my overlap distance times my string constant. But I need to also multiply that by norm R. Okay, so let's see if they're overlapping and I'm going from A to B. I think that should be a negative number. I think this will work. And then FB equals negative FA. And that should work, right? This is an important point up here, is that if they're not overlapping, every time I go back and set the force to 0, and then I'll only calculate the force when they're overlapping. Let's see what happens. I'm a little scared. Okay. So, I think that worked. How do we know that worked? Well, I already said, if momentum is conserved, it should work. So let's plot the momentum. G1 equals graph, X tidal equals time, Y tidal equals px in kilogram meters per second. And then we'll do FA equals G curve, color equals color dot blue, FB equals G curve, color equals color dot red, and then FT for the total is just, it'll be black, G curve. Okay, so now down here, let's plot those. So I'm going to say FA dot plot T ball A dot P dot X. I can't plot the momentum. I can only plot one of the components. FB dot plot T ball B dot P dot X. And the total FT dot plot T ball A dot P dot X plus ball B dot P dot X. Did I ever save it? Okay, so there's my total. You'll see here that ball, the blue one is ball A. Oh, it had some momentum, and notice the initial momentum for ball, the other one was 0. And then when they collided, they're both moving, but the total momentum stayed the same as the initial momentum before. Okay, and they have equal and opposite momentum, so that seems to work. Now, what if it's not a head-on collision? So I can fix this, right? If I have that ball and I want to have it come in, what if it's not quite at an angle, but it's shifted up a little bit? In that case, when they overlap, the vector between them is going to be at an angle. So I can just do this. Ball A, let's give it an initial position of 0.01. I think they should still overlap in the y direction. Okay. Let's see. I mean, awesome. Yeah, that's awesome. And the momentum is still conserved. That's good. Let's check the momentum in the y direction. I'm not going to change the title. I didn't. I did px. Y, 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 y. What if you want both of the balls moving beforehand? Now, there is a slight problem. If you want both balls moving, you have to be careful because they could miss each other. If I have them going head on at like this, they're not going to miss. Okay. So I can just give, or I can have them both move in the opposite directions. So let's move this one. Let's do fun. 0.04. So one ball's moving that way, the other one's moving the same way but slower. Is momentum still conserved? Yes, it is. Notice in the y direction, the initial momentum is 0 and the final momentum is 0. So this does indeed work. Now, I have a couple things. One, what if I do this? I could do this. If they overlap, I still need that vector r. I could just say, I can't believe I got the direction right. Did I get the direction right? If I got the direction wrong, it still works. So, no, I did because it bounced up. Okay. So let's say FA equals some value, some constant value, some constant force. Let's say 1. Let's just say norm R. FB equals negative norm R. So it's just it's going to have a force of 1. It doesn't matter how much it overlaps, it's the same force. Let's see what happens. Okay, something weird happened. Oh, I didn't do negative. That's right, this has to be negative. That's fine, it's still, momentum was still conserved. Okay, but what happens is they pulled each other towards, and that's kind of weird. But let's see, let's make this one negative, and that one positive. And so you see that the collision looks essentially the same, and that's kind of cool. Now, it is possible that if I go back to my old way, let's just put this at a smaller force, 0.1 times, and let's just say this is equal to negative FA. Oops. Okay, that looks kind of cool. Let's make it a little bit smaller, 0.1. Okay, so that was a good collision. I really like that. Because notice that they pushed apart when they were overlapping, but it wasn't enough to really kind of prevent them from passing through each other. So it passed through it. But still momentum is conserved. It doesn't matter. As long as those two forces are for the same value in different directions with the same amount of time, it's a momentum is conserved. Okay. Let's do one more thing. This is an elastic. Is this an elastic collision? Well, we would know if the kinetic energy is constant. So I want to plot the kinetic energy before for the two things. So let's just change this to K in joules. And I have to change the units. If I don't, I just feel like I'm a bad person, and I don't like being a bad person. And I'm going to put this back to the springs. It could be a gravitational interaction. It could be an electrostatic interaction. They don't even have to overlap. And I'll do that in a future video for fairly soon, and we can see what that looks like. Okay, let me run this to make sure things are working. Okay, so I want to calculate the kinetic energy before and after the collision. So down here, I'm going to say Ka equals mag 0.5, mag ball A dot P squared divided by 2 times ball A dot M. It's P squared over 2M, right? The kinetic energy is P squared over 2M. I can't just say V squared or 1/2 mv squared because I never calculated V. I use momentum. So let's do the other one. KB equals mag ball B dot P squared divided by 2 times ball B dot M. And then that's fine. So now over here, I can plot. I don't have to, the kinetic energy is a scalar, so it's just Ka, Kb, Ka plus Kb. Okay, so there's my kinetic energy. This is great. I love this. I love this because look, is it elastic collision? Yes. Right up here is the total kinetic energy. Black is the total kinetic energy. The kinetic energy before, the kinetic energy after, the same. But it's not always conserved. It's not always conserved. Look at this little spike down right here. Then the kinetic energy drops down. And that's because they did slow down for a very short amount of time. Some of the energy went into the spring potential energy stored between those two things. And so, but then it got it back. So if you look at right before and right after, kinetic energy is conserved. But it's not 100% conserved, period, right? Energy is conserved. If I plotted the spring potential energy in there too and made the black thing the total energy, it would be conserved. And it should always be conserved. So, but kinetic energy is only conserved in these special elastic collisions. Okay, what about inelastic collisions? It's a little bit more difficult, but we can still do that. And we'll do that in the next one. But there you go. Code down below. Playlist for the whole thing, because this is part of my Python for Physics series, is down below. So you can go back and watch the other ones. And I'll see you again.